Alright, so this is Unit 6, Lesson 4. So we already have our 5.1, 5.2, 5.3. This is our last lesson, statistical simulations. So simulation is a way to model random events such that outcomes closely match real-world outcomes. By observing simulated outcomes, researchers gain insight on the real world. So then, why would we use simulations? Is the question. It's a good question to ask yourself. Number one, situations do not lend themselves to precise mathematical treatment. Number two, situations may be difficult, time-consuming, or expensive to analyze. In these situations, simulations may approximate real-world results, yet require less time, effort, and/or money than other approaches. How to conduct a simulation. Simulations are useful only if they closely mirror real-world outcomes. So, steps required to produce a useful simulation are, we'll go down the line, Lainey.
Describe the possible outcomes.
Kenzie.
Link each outcome to one or more random numbers.
Shelby.
Choose a source of random numbers. Choose a random number.
Based on the random number, note the simulated outcome.
Repeat steps 4 and 5 multiple times, preferably until the outcomes show a stable pattern.
Analyze the simulated outcomes and report results.
On average, suppose a baseball player hits a home run once every 10 times batted. Then suppose he hits exactly 2 at-bats every game. Using a simulation, estimate the likelihood that the player will hit 2 home runs in a single game.
All right, thank you. So the possible outcomes here would be hitting a home run or not, right? Those are really the only two outcomes we're interested in. Hitting a home run or not. Step 2, similar to what we did with the cup game at the carnival, assign outcomes to random numbers. So we'll need to choose a random number to represent a home run. Now in this case, we're not talking about a 6-sided die. We're talking about all the possible digits, 0 to 9. So what number would you like to assign to a home run? Anyone shout it out? Pick a, what number? 7. So a home run would be a 7, and then not a home run would be a 0 through 6, or 8 through 9. Step 3, you need to choose a source for your random numbers. In this case, so we can all use the same random set of numbers, I've already tracked down a source for you here, the Stat Trek random number generator. Here it is. So we've generated here 500 two-digit numbers. And the random number, note the simulated outcome in this example. Each two-digit number represents the 2 at-bats in the single game. Remember, our baseball player only bats twice. So since the digit 7 represents a home run, the number blank blank represents 2 home runs in a single game. 77. Any other two-digit number represents a failure to hit consecutive home runs in the game. So the table here shows 500 two-digit numbers, thus 500 repetitions. So count the repetitions of 77 and create a ratio of the number of 2 home run games. So that's going to be out of 500. So go ahead, find how many 77s are there in all of these randomly generated numbers. When you think you know, raise your hand. What do you think?
6.
I have a 6. Does anybody get more than 6? Did anybody else get 6?
I got 6.
All right, we'll go with 6. Congratulations, you're the winner of a new pencil. This is the new one.
That was a much better try.
Thank you. All right, so 6 out of 500 rounded to the nearest hundredth. What do we get? 0.06.
0.01.
0.012, okay. So that's the nearest 1,000. That's cool too. So that'd be about 1.2% of the time we could expect for a baseball player to hit consecutive home runs. It's pretty good. Example 2 messed up on me. Not sure what's going on here. But it should say drink sizes or coffee sizes. In this simulation, in this observational study, 4/10 of the customers wanted a 12-ounce drink, while 6/10 of the customers, or 60%, wanted a 16-ounce drink. What would be a valid assignment of digits? Again, considering the digits 0 through 9.
So
I like 0 to start.
0 through 3.
Okay.
Which means a 12 ounce. 4 through 9.
Okay, so 4, 5, 6, 7, 8, and 9. So 4/10, so that would be 4 out of 10. There are 10 digits. So it makes sense. You could randomly assign any 4 digits and the remaining 6 digits to the 16-ounce. It's kind of nice to do it in a logical fashion just because it makes it easier to observe. So then, in this simulation, we could then pull up a random number generator and start generating numbers. And again, like we did with the carnival game, do a simulation, which tends to be more true to life than sometimes doing theoretical statistics, because we notice that rarely is it exact to what we would theoretically find to be the probability. That's your last notes of the year.